all, I would like to thank Claire and Jose for organizing this winter school and for giving me the opportunity to give lectures. So I'm working at the MPI Institute for Quantum Optics in Germany, in the group of Chirac. I'm a theorist, and I've been working on quantum mechanics there. This proposal for levitating the mechanical space, and I will talk about this in the lecture. But today I will start with this general idea of quantum mechanics at the limit. So the plan is the following, actually of the lecture. So first I would give like quite a long presentation and discussion of the possibility of testing quantum mechanics with quantum superpositions of massive objects. Then I will explain a protocol that allows to prepare large superpositions of massive objects. And I will discuss this in a very general fashion without specifying any particular physical interpretation. And just discussing some unavoidable sources of decoherence that we always have. And then finally I will also talk about these proposals for doing quantum mechanics with an optically levitated electric ionosphere, as well as magnetomechanics with a magnetically levitated superconducting microsphere. Let me start with motivation. And so what I want to say is that the archetypical motivation for quantum nano and micromechanical oscillators is the following, that we always see in papers and many talks. There are three motivations for these mechanical oscillators, this massive object that we can go to the quantum gravity. The first one is for metrology, or for sensing, like for example, heat trappers, as mentioned. Typical examples are mechanical oscillators for gravitational wave detections, but also for smaller things like weight, very small mass. And we will hear also a lot of motivation in the lecture by Andy Gerassi, that will come tomorrow. And the second one is the possibility to use these mechanical oscillators as a quantum transducer to couple quantum systems of very different natures. And I guess Raul will also talk about this. He has a nice proposal where, for instance, on parallel, on a side of the mechanical oscillator you put some charges, on the other side you can put a magnetic tip, and then, for instance, you can couple spin, qubit, for instance, with the charges, you could couple that to an ion or something. You can really transduce coupling between very different systems. And finally, there is always also this idea that people say, since you have this massive object, really like a microscopic object, you can maybe use it to study the foundations of quantum mechanics. And I would like to focus on this part here, since this will be covered lectures. And the first comment I want to say is that when we say that foundations of quantum mechanics, what do we actually mean? So there are many sentences that we use and say, like for instance, we will prepare macroscopic quantum superposition. What does that mean, macroscopic? We will prepare Schrödinger cat states. We will study the classical quantum transition. We will do experiments of fundamental interest. Maybe test gravitationally induced decoherence. Test unknown source of decoherence. What do we actually mean with what we do? I will try to clarify with my opinion, of course. So, but for this, let's go back to the basics. Okay, so if we want to test a theory, so we have the scientific method. Okay. So what we do is we have a theory. From the theory we can have some predictions. Then we do experiments and we see whether we falsify the predictions. If we don't falsify, we are just corroborating the theory. But if we do falsify the prediction by the experiment, then we falsify the theory. We know that the theory is wrong. So the first question that we have to ask is which theory do we want to test? So here there are two options. Either we test quantum mechanics, that's what I will discuss in these lectures, or we test other theories. And actually, you will see by the intervention of Andy Gerassi proposing to use mechanical oscillator to test maybe different theories in high energy physics that predict a correction of the Newtonian force at very short distances. And then when he gives experiments, he wants to test other theories. Okay. But here, let me focus on testing quantum mechanics. And therefore, in this framework, we have the following. So we know that the theory of quantum mechanics gives you this prediction that there is a quantum superposition principle. And then we want to do experiments and see if we see the superposition. Okay. Of course, we have to, so the question is, do we see the superposition? If we see it, okay, then we just corroborate the theory. That's okay. If we don't see it, and we know that there are no standard sources of decoherence that prohibits us to see this superposition, then we falsify quantum mechanics. Of course, this would be a big thing. Okay? But that's a scheme. And therefore, if we have this parameter space, okay, so what we do experiments, we have checked the theory of quantum mechanics in some parameter space, and what we can do is we can just increase the area where we have tested the quantum mechanics, but there is a big area that we have not explored. And therefore, what we want is really to push the boundaries of quantum mechanics, let's say. But there is a very important question here, two questions. The first one is, why do you want to test this? Why are we expecting that this theory should not be correct? And the other one is, okay, where do we explore? Because now explore quantum mechanics in very different ways. We could say, well, I want to test whether the superposition principle is valid in Arizona, in the desert, for instance. Or to check whether the quantum superposition principle is valid underwater. So if place is this interesting. So you could test quantum superposition principle in many different ways, but the point is to identify where it's interesting. So why should we explore quantum mechanics? So many people, many scientists say that there is this measurement problem in quantum mechanics, which I share the opinion that this is a problem, and the way I understand it is the following. So we know that in quantum mechanics we have two dynamical evolutions for systems. Either just a unitary evolution, given by a Hamiltonian that evolves the state of my system in a unitary way, or the action in which we make a measurement and then the state collapses. This is a non-deterministic evolution, non-unitary evolution of my wave function. The problem is that what about if now you take into account everything? So the system that you will measure plus the apparatus that you're measuring, and you consider all the degrees of freedom that are taken into account in this process of measuring, right? Which is something you can do. I mean, at the end, experiment is something you do in the lab. So if you take into account all the degrees of freedom that are involved in the measurement process, and you describe the wave function, you let it evolve, then what's happening? It will be evolved in a Hamiltonian, therefore everything is unitary. Or, so how do you describe the collapse then? And one question is, well, so the point is that, okay, let's start to put all the degrees of freedom that you take into account, for instance, in a Stengel-like experiment. You have the electron goes, and at some point touches the surface. But what does it mean to touch the surface? Okay, let's take into account all the degrees of freedom in the surface that describe the interaction. And then the surface is connected to, to more things, to the room, and then you start to grow. And then the question is, would you end up with saying that the whole universe with all the degrees of freedom is evolving as a pure state? Well, many people say so, but of course I find this somehow not very intuitive with the fact that if this is the case, then you should take into account gravity, right? Because of course, as soon as you involve very massive objects, and for sure gravity is there. We don't have a theory that unifies gravity and quantum mechanics. So how do you find this thing? So that's why I think this brings a problem somehow. And then the whole is, okay, that so if we start to explore quantum mechanics, maybe there is a region where you really see like a breakdown. Then quantum mechanics is not valid, and then we have to change our understanding of the theory. And then the second question is, where should we explore quantum mechanics, as I said before? And to my opinion, there are these, what is called these collapse models, that many people have proposed, which somehow provide a very nice roadmap to tell you where to explore quantum mechanics. And then the scheme is this one. So collapse models give you like a roadmap that tell you, okay, so let's try to test quantum mechanics in this parameter region. And what I want to say is, I will briefly talk about these collapse models, and they are not theories, so these are not rigorous theories derived from first principles and really consistent that give you the prediction that quantum mechanics breaks down at this place. But somehow, sometimes they give you some conjectures or waving recommendations that are quite intuitive. And I wrote this paper where I describe different collapse models and how to test them using superpositions of quantum superpositions of massive objects, which somehow summarizes the first lecture. And the idea is the following. So let's assume we have a massive object, a sphere, for instance, of homogeneous density, and the emitter capital D. And then we prepare a superposition where the center of mass is separated by a distance small. Yeah, and these are the two parameters. The diameter, which tells me basically the mass of the object, and the superposition size, which is the distance between the center of masses. Then there is this model, the so-called continuous spontaneous localization model, which was put forward mainly by Girardi, Rimini, Weber, and many other people like Bell, Gizen, basically back in the 70s, 80s, something like this. And what they tell you is they make a modification of the Schrödinger equation. They say, okay, let's assume there is an additional term into the Schrödinger equation, which is stochastic and nonlinear. And they had just added completely ad hoc. Okay? And this term basically says, well, it's motivated by the fact that, okay, is quantum theory actually exact? So is the Schrödinger equation the most fundamental equation in quantum mechanics, or maybe there is some additional terms that you see with the experiments we typically do, they don't show up, but maybe at other parameter regimes they typically show up. And well, and that's what they did. And this is just a mathematical term that they add, and the intuition is that what it does is that it contracts the wave function at a certain rate. So you have a set position of a particle, so whenever it grows above some distance, then boom, it contracts it stochastically with a certain rate, and also it localizes the wave function into some given size. Therefore, there are two parameters here. One is the rate of contractions, and the other one is the size at which you focus the wave function to contract. And these two parameters are completely phenomenological, so you just have to include it by hand and bound it by experiments. But nevertheless, they propose the value. So these are the two. So this is the distance, a length scale that tells me how much I contract the wave function, and this is a frequency, that is the rate of contractions. And for instance, this parameter, so they proposed this value. So they said, okay, let's some kind of hand-waving argument. They suggest, okay, let's assume the contraction is of the order of 100 nanometers, and the rate for a single nucleon is of 10 to the minus 11 hertz. But then if you have a more massive object, this rate will increase. Actually, the way it increases, with some mathematical arguments, it goes with the mass to the power of 2. Okay? So then, for a larger mass, this rate would be higher, so it will contract. So then the superpositions will become faster. And then there are many experiments that somehow put bounds to these parameters. Just to give you here, this is taken from the review I showed before. So here, what is this number? What this number means is, imagine this value here. I multiply this value by 10 to the power of n. Okay, and n is the number here. So this means that, for instance, the Fuller-N diffraction experiments done in Vienna, by Marcus and Heidegger, about this Fuller-N molecule of 60 atoms, and then they do the superposition interference. I will talk about it later. This gives a bound to this value, which is 10 to the 13 times this number. Then there are other experiments, for instance, like the proposal like Dirk-Momister to prepare a superposition of a cantilever, 0 plus 1, which would give an hour of time. So you see that different experiments can give you different values. but we are still far from getting really to go to zero and go to zero. So to try to falsify the model with the original value of the contraction rate. So then there is another model which is also famous, which was given by Penrose and also Diochy, which, let's say, is less mathematically formal, but more intuitive, and it has advantages. It is parameter free, because the other one is not very nice. It depends on what parameter. And the intuition he gives to derive this collapse model is the following. So imagine you have a massive object here, this kind of slab, and then you prepare the position. Okay, one position is this one, and the other one is illustrated by the dashed area. And you see that there will be two regions which are non-overlapping, right? If you consider this as being two different masses, let's say. And you take non-overlapping areas of mass or volumes of mass, and you compute the gravitational interaction energy. And this is an energy scale, and basically this energy scale automatically gives me a time scale for the decay, for the decoherence, right? And then, this gives me some kind of decay rate. And this depends on the mass and also on the superposition size. And actually from this argument you can also kind of put it into a master equation, which I will describe, which is called this Newton formula. But what is nice from these predictions is that you see that they give you the following idea, or they predict the following. So they say, well, if I would have this type of objects and this type of superposition states, they will tell me that if I have a small mass, okay, I can have very large superpositions where small d is much larger than capital D, so really delocalized, and then the state will be completely stable. Whereas if I have a more massive object, and then the superpositions comparable to the size of the object, they will be very unstable, and you would not be able to observe superposition, and then quantum superposition will be falsified. And I want to emphasize that this absence of superposition principle has nothing to do with the typical decoherence in quantum mechanics. Standard source of decoherence are something that is beyond quantum mechanics. So this is even in the perfect case of being completely isolated from the environment, you will not be able to compare the quantum superposition for such a massive object and such a superposition size. Okay. Very good. So that's the scheme. And what I want to discuss now is a type of decoherence that is called position localization decoherence that will be very useful to describe the protocol that I will do afterwards, because it accounts for the type of decoherence that you encounter in standard sorts of decoherence as well as the decoherence given by these collapse models. Okay. And this is a very kind of standard source of decoherence and very well studied in many books because it accounts for typical standard source of decoherence. And the idea is the following. So imagine you have the state you describe it by a density matrix, so you will have a master equation, and now you describe the density matrix in position representation, basis. Okay. So then if you compute the correlations between x and x prime, okay, so this is the coherence in position, you have, first of all, the dynamic, the unitary evolution given by the Schrödinger equation, plus a term that will basically make the correlation in position decay. Okay. And this is the decay rate. Basically, what this master equation tells me is that the diagonal terms of the master equation of the density matrix in the position basis decay exponentially in time with a rate that is given by capital gamma. And as I said before, this describes very well sources of decoherence such as the scattering of air molecules. You have a massive object, and then some particle comes and interacts of the particle, and this particle carries away information about the position of the object, and this produces some decoherence into the wave function. And also black body radiation. So any object has some temperature, so it emits photons, and each of these photons provides information about where the object is to the environment, and this creates very well described by and also, collapse models can be put in the form of this master equation. So that's why it's very useful to discuss this source of equations. And what is very important, or very useful, is that this decay rate, so the decay rate here in the master equation, can be very well approximated by the following function. This one here. You see? So this function, plotting, so what it does is in the beginning, for distances smaller than this parameter, basically 2 times a, okay, it increases quadratically. Because I expand the exponential and I have a quadratic term which grows the decay rate. Meaning that if I look at correlation, for instance, if I have a superposition, the larger the superposition is, the faster it will be coherent. Makes a lot of sense. That at some point it saturates. See, when this has to be large, then basically it goes to a constant value. Therefore, there are two parameters. One is the localization rate, this frequency here, and the other one is the localization distance, so the distance upon which it starts to saturate to a constant rate. So then there are these two limits, the short distance, I repeat because I will mention this very often. It goes quadratically, and the long distance in which it saturates. And then actually you can, from these values, you can define also this constant of proportionality here, which is typically called the localization parameter. It has units of frequency divided square root square root and integer square. And actually, just for those who are familiar with master equations, so in the short distance limit, when you have this decay rate, the master equation can be written in this form, in this Liebland form, which is it's a very well-known master equation, which is of the type of Gaussian physics, because you see basically here the jam operator is the x position, meaning that the environment is measured in the position. Okay. And this is quadratic up to quadratic in terms of operator configuration annihilation. And this is typically yields only Gaussian physics. You can do many analytics from this. Okay. So as I said many times, so to remember, there will be of the AMO terms in position-based decay exponentially. There are two parameters which are relevant, and the short distance goes quadratically, and the long distance saturates. And now you can compute these parameters for different sources of decoherence. For instance, with L molecules, the localization parameter, which is the constant that goes with the quadratic part, it scales. You can obtain this value, and here the most important thing is that it goes with the surface of the object first here, and with the pressure. And this makes a lot of sense because the L molecules basically what accounts here is the cross section for the scattering processes in which an air molecule collides with the sphere, and it goes with the surface. And also the pressure here is like it is giving me a magnitude of the echo, of the flux of scattering events. And then also, what is very intuitive and what makes a lot of sense is that the saturation distance is given by the de Broglie wavelength. And the reason is the following. So imagine I have a superposition size that is larger than the de Broglie wavelength of the scattering particle. So then the scattering particle that go away can resolve the superposition size. Therefore, with one scattering event, you already provide maximum information to the environment, and then you destroy the superposition. Whereas if the superposition size is much smaller than the de Broglie wavelength, with one single scattering event, you don't resolve the superposition. So you just, by having more scattering events, you start to create more decoherence.
Is this for air in like an atmospheric pressure, like viscous, like flow regime, or is it like a ballistic brooding at like lower pressure?
Yeah, so this is more at lower pressures. So this is assuming, because if it's higher pressures or higher density, then of course there is a given viscous.
Yeah.
This would create more decoherence. So that's even in the assuming I have a very good vacuum and there are only very single scattering events from time to time, this is also very relevant. Then there is another one, which is black body radiation. The fact that the sphere has some temperature and it emits volume. You see that first this goes with the volume, because when the particle is smaller than the wavelength of the photons that it emits. It does not scale with the surface, as is typical with black body radiation, but with the volume. And in this case, it also goes with the internal temperature, to the power of 6, and basically the electric constant, the imaginary part of the electric constant. And in this case, the thermal de Broglie wavelength for the photons that you emit at very low temperatures, so for instance 4 kelvins, this is of 1 millimeter. And I forgot to mention here that the thermal wavelength for air molecules is 0.1 nanometer. Typical. Yeah.
So the black body term doesn't contribute unless the object has a motion?
So there are 3 types of contributions due to black body radiation. One would be emission, the other one would be absorption, and the other one would be scattering of thermal photons. Yeah, and by far the most important contribution is emission. The emission of photons. Yeah.
Okay.
Yeah. When you put the numbers, you can have. So let's say you have the same expression for the 3 cases, so you can have and compare. Actually, this one is for absorption and emission, depending on whether the temperature is the temperature of the bulk object or the temperature of the environment. And what is important here is that the thermal wavelength, the Broglie wavelength is very different. You see, so for air molecules it's very small, 0.1 nanometer, meaning that I will saturate the decoherence very fast. So as soon as I have a superposition larger than 0.1 nanometer, basically the decoherence rate will not increase with the size of the superposition. Whereas with black body radiation, it always increases by growing the superposition. And then now I can compare with collapse models, for instance, as I said before. The CSL model, basically it scales with the mass, so R to the 6. Okay, it doesn't matter here, the particular expression. And the saturation distance is 1. And the Penrose model, it actually scales also with R to the 3, with the volume, and it saturates when the superposition distance is larger than so when the two spheres do not overlap. Okay, so as soon as they do not overlap, then the decoherence does not increase anymore. And why I wanted to put this table already here in the motivation of this detail is because of the following observation. So you see the scale. So here, as I said, this goes with the surface, with the volume. This depending on which if the object is smaller than 100 nanometers or larger, so it's typically, let's assume it's larger, so it goes with the surface or with the volume. So now if I take, for instance, the decay rate superposition of an object that is separated, is for instance of an object which is of this type, a massive object trapped in a potential, in which you put it into 0 plus 1, superposition of 0 Fock state plus 1 Fock state, 0 phonon plus 1 phonon. The decay rate will be given by this capital lambda that I discussed before, multiplied by the ground state size to the square in the harmonic oscillator. And this is, remember, this is square root of h bar divided by 2 times the mass omega. So to the square, it means that this scales like 1 over the mass, 1 over the volume. Okay. So then you have lambda divided by the volume. And as I said before, here, basically at max, you grow with so lambda scales with the volume. So then this means that, so I mean, this somehow is against the intuition that one would have, that I would say, well, if I have a very big mechanical oscillator that I prepare into the ground state and then I prepare a superposition of 0 plus 1, I would say this is really macroscopic. Well, I mean, it's against this intuition because you see it does not scale with the mass in the best case, and in the worst case it actually decreases. Because whereas the localization rate does increase with the mass, the superposition size decreases. So the wave function is really, really very much localized. So therefore the overall decay rate does not increase. And that's very relevant, for instance, if you want to test collapse models, like the Penrose model or the CSL model. It doesn't, so this is telling us that it's not enough to have a very large mechanical oscillator into the ground state and then prepare a 0 plus 1 to test collapse models, but you have to, you see, you have to grow the superposition size. Otherwise, you will not be able to test it. And actually, according to this definition, the state would be more microscopic, even though it has a larger mass. Is this point clear? No? That's kind of important because I also find a bit provocative this argument because many people say so that we say in the field of quantum mechanics that we do macroscopic quantum mechanics because we have a very large mass and we can maybe prepare superpositions. But, okay. So then the message here is that larger superpositions are needed. Okay? And therefore these collapse models provide a definition for macroscopic superposition. Because for me now macroscopic will mean that I'm able to test better these collapse models. And actually by putting some numbers, you see here I'm plotting for different sizes of spheres and for different superposition size, superposition length, what's the decay rate. Okay, for the CSL, for the DHT level. For instance, you see that if you take a sphere of 300 nanometers volume, then if I have a superposition of 100 nanometers, then this will decay 1 millisecond. But if I have a very small, well, if I have a 100 nanometer sphere, then you see I'm in the second scale for the decay rate. So it really shows that in order to make this collapse model acts very strongly, then I have to go to larger masses and larger superpositions. It's not enough to go to larger masses. And for the Penrose model, also the number it's weaker. It's much weaker because you see you're dealing with spheres of maybe 1 micron or 2 or 3, so a few microns, and they need to be separated of the other, also a few microns in order to go to the millisecond region. And as I will discuss, this also looks not so impossible because if you also look at the decay rate allowed by scattering of air molecules, which always will be there for any good vacuum. So you have, for instance, if you have very good vacuums of 10 to the minus 12 torrs, 10 to the minus 18, 10 to the minus 14, you can have also decay rates which are much higher than 1 millisecond, almost going to hundreds of milliseconds for spheres of 1 micron. And for instance, 10 to the minus 15 torrs, 10 to the minus 15, 10 to the minus 14. Okay, so this looks kind of promising in the sense that by having a sufficiently low pressure, you could enter into a regime where you can start to think about testing this collapse model. And regarding black body radiation, as I will discuss later on in the lecture in more detail, you see, so that's also the typical decay rate that you have in terms of the bulk temperature of the object. And that's a bit more demanding because you see, if you are at room temperature, then the decay rate would be 5 milliseconds. And if, for instance, you manipulate your object by laser light and then you heat it up at a much higher temperature, the room temperature, then it would be very much limited. You would have very few milliseconds of coherence to do your experiment. However, to motivate why at the end of my lectures I will talk about superconducting microspheres, if I can use objects which are really cold, 4 kelvins for instance, then I have a huge amount of time, of the order of seconds. And this is one of the motivations of why I will talk about superconducting microspheres. Okay, so that's a bit the summary. So the idea is that, well, collapse models are suggesting that we should use large masses and also large superpositions and test quantum mechanics in this regime. This might be interesting because somehow we predict that this would, that maybe quantum mechanics would break down. So I think that give us a roadmap where to do experiments, interesting experiments to explore. But I want to emphasize this time because it's also important. It's not sufficient to have large mass, but also you need large superpositions. But the question is, okay, so that sounds very good, but, and this looks like a, who would start to do this type of experiments that maybe take a lot of time to do, and they are high risk because, of course, when you do the experiment and you see the superpositions, that's very nice for sure, but it's not clear that you will observe the breakdown. So is it only a high risk, high gain project, say that this is not the case because of the following. Basically, the typical scheme to prepare a superposition is the following. So you have a center of mass, you manipulate, then you have to run out a protocol and create a superposition. Okay? First of all, you see that in this scheme, you have to fight against decoherence, because already to have a very large mass and the quantum regime is demanding, then you have a protocol to create a superposition. Because you have to do it in a coherent way, such as we have destroyed coherence. And then if you prepare the superposition, you have to be able to observe it. It's also very challenging. Okay? So you have to fight against decoherence. And the other one, which is also very important, is that the protocol requires always a nonlinearity. Because the typical state you start is a Gaussian state, like for instance the current state of the harmonic oscillator, and you want to end up into a Schrödinger head, for instance. And this requires a non-Gaussian operation, or a non-linear operation. An operation that is, in terms of operation and relation operators, is terms which are higher than the These terms are always very demanding, very difficult to obtain. And this nonlinearity has to be very strong to create such a large superposition. Then this means that there will be side applications studying or doing this type of experiments, which are not only fundamental. The first one is that for sure you will devise or you will design very strong nonlinearities that you for sure can use for other things. It's very interesting quantum optics experiments. And the other one is that since the whole protocol or the whole state is so sensitive to the environment, it also means that it's extremely fragile to the environment. And therefore you can exploit it to maybe design very good detectors. And actually, you see very, very nicely by this illustration, which is that if you would be able to prepare such a large superpositions where the masses do not overlap, then actually what you are doing is you are creating a new state, that is called quantum optics, meaning that you would have an interferometer where you put all the atoms in either in one branch